Stefano, can you share your slides yourself?
Yes, can you hear me?
Yeah, I can hear you very well, thanks.
Okay, now let me try and share my slides. Yes, here it is. Okay, now what do you see?
Stefano Frixione on Monte Carlo at NLO-Delta.
Yes,
So I can
now
see.
the point is that recently when I used AcroRead, I seemed unable to go full screen. So is that disturbing or is that okay?
I think, I mean, it's not full screen, but I think it's okay. I mean, I think it's a large enough font, so it shouldn't be a problem, I think. Does anybody have problems seeing what's there?
I think it's fine.
I guess the toolbar on the right could be closed, but it's fine.
Yeah, I was trying to do that. I'm not sure I can, but again, it's okay. Well,
otherwise, just go ahead like this, Stefano.
Right. Yeah. Before starting, you know, the answer to James' question before is no.
I thought you might say that.
Yeah. So it's a short answer, and okay. So thanks for the invitation, and you know what I'm going to talk today is essentially based on this paper which Josh already mentioned. Let me start by saying that MCT NLO-Delta is an MCT NLO inspired matching formalism, and it aims is preserve the good features of MCT NLO while getting rid of the not so good ones, which are essentially the negative weights. In general, I mean, although the matching formalism is different from MCT NLO, you can largely say the same thing in the comparison of MCT NLO versus POWEG as for MCT NLO-Delta versus POWEG. So I will not talk about this thing any further here. Okay, so the primary goal is the reduction of negative weights, okay? And there is an expected primary beneficial side effect, which is that the shower scale assignments are much more meaningful from a physics viewpoint with respect to those in MCT NLO, in POWEG, in essentially all of the generators that are currently used, okay? So let me start by saying that we are only talking about money. It's not physics. I mean, negative weights has nothing to do with physics or with conceptual issue. It's just a practical issue that increases the cost. So, I mean, these are equations taken from the paper. If you denote by n plus and n minus the positive and negative weights in n event generation, you can define the efficiency, which is 1 minus 2 times the fraction of negative weights, and this is a number between 0 and 1. So the key thing is that in order to have the same statistical accuracy as for an M event positive generation, one needs to have a number of events which is CF times larger than M, okay? And this CF we call the relative cost. And this is a factor which is not small. I mean, this is a plot for 3 versions of this relative cost, depending on the correlation you assume between negative and positive weights. Usually people neglect the correlation between these two things. And so let's say that you take 0%, which is the most favorable situation. Still, this implies that if you have a 10% or 20% or 30% negative weights, you get a cost which is 1.5, 3, and 6 times larger than with only positive weights. Okay, so there is indeed a strong motivation to reduce the number of negative weights. Having said that, I think we all agree with that. Having said that, let me also stress that although negative weights are a very unpleasant feature of these simulations, they must not be used as an excuse to give up on accuracy, okay? I mean, if you remember the famous discovery of SUSY at the start of the LHC, I mean, this was due to the fact that, essentially people simulated 10 jets with PITIA back in the 90s, okay? And this leads to a discovery. I mean, now the situation is not as striking as in that case. But precisely because it's not as striking, you want to go to high precision physics, and therefore, giving up on precision is simply not an option, I believe. So, having said that, of course, with the same accuracy, with the same physics accuracy, you want to reduce negative weights as much as is possible. Okay, so let me remind you how MC10LO works, because this is essential to understand how MC10LO-Delta works. You have the generator of the shower, which is composed of two events called the S events and the H events. S events has n+n body kinematics at the cross-section level. H events have n+1 body kinematics at the cross-section level. And the cross-section is essentially the same one as you have in a fixed order computation, namely this piece plus these pieces here, plus minus the same thing, which is what the Monte Carlo would do if left alone and if expanded at order NLO. Okay, so that's all there is essentially. Okay, now, so in order to convert your preferred fixed order computation NLO into an MC10LO computation, what you do is to establish what the Monte Carlo does at this order in alpha, which is completely, in the hands of the Monte Carlo authors, except for some controllable inputs, the most flexible of which is the shower scale. So in MC10LO, in the most recent versions of the MC10LO, what we do is to exploit this flexibility in order to assign a scale between two given hard scales associated with the process. Okay, and this is done in a event by event and essentially random way. But still, these two scales M1 and mu1 and mu2 are fixed and of the order of the hardness of the process. Okay, so where do the negative weights in MC10LO come from? There are three classes of negative weights. First of all, let me introduce a pool, which is essentially a measure of how far you are from the Born kinematics. And this could be, for example, the recoil PT in Dralian. So you measure the PT of the lepton pair, and the farther you are from zero, the farther you are from the Born configuration. Okay, and let MH be the typical hard scale of the process. In this case, the invariant mass of the lepton pair, for example. So you have three classes, which are H events with the PT much smaller than the hard scale, H events with the PT of the order of the hard scale, and then S events. There is a crucial difference between these three classes, essentially, is that those stemming from H events are due to the physics of the MC10LO, whereas those stemming from S events is essentially due to a choice in the generation of events, which is otherwise convenient, but not so practical from the viewpoint of negative weights. So let me start from that. The crucial thing is that, as I said before, S events have an n-body kinematic, so the same as Born. However, the cross-section they are associated with as a support in an n+1 body kinematic. So generating things like this, that is, you integrate the cross-section in n+1, in the phase space of n+1 body, is the same as first integrating the cross-section on the 3 degrees of freedom, which are not associated with the Born, and then generating the kinematics. This was called folding by Nazon in 2007, and the idea is more general than MC10LO events. For example, it's also used in Power Box in order to reduce the negative weights there. Okay, so this has nothing to do with the physics. Again, is the way in which one chooses to generate S events. H events have a more complicated case because this is the simple cross-section for H events. As you see, you have negative weights when the Monte Carlo counter terms are larger than the fixed order cross-section. This happens especially when you're close to the region where the Monte Carlo dominates, okay? And this is a pity because in that region there, the H events are essentially useless except for rates. So, you're really wasting your time to figure out what's the distribution of those H events is, because that will be compensated by the much larger contribution of S events. So in pictures, what you have is that your short distance cross-section for H events is the blue line here. So that goes negative at small PTs. But this is then completely compensated when you turn on the shower, because the shower is dominated in this region by S events, which are largely positive and therefore, compensate for this blue line in order to give you the final physical prediction, which is the green line, okay? So essentially, all what you do here is a waste of time, essentially. So the idea of MC at NLO-Delta is to get rid of these events here before showering rather than after showering, okay? So what you do is essentially write the same, generating functional as in MC at NLO, with, however, modify the short distance cross-section. So this in parentheses was the former H event cross-section for MC at NLO. The only thing that you do is to multiply it by a delta factor. The same delta factor you insert in the S events in this way here. And this is essentially dictated by unitarity. So you are really constrained to do that in this way. Otherwise, you screw up the properties of MC at NLO, and I'll return to that later. So for the moment, the only thing you need to know is that this delta is a factor which is between 0 and 1. Formally, if you expand it in alpha strong, it is 1 plus order alpha strong. It approaches 0 in the soft and collinear limits, and it approaches 1 in the hard regions. And this is all there is, essentially, in these formulas. So when I say that MC at NLO-Delta is inspired by MC at NLO, you see why. I mean, it's very close to MC at NLO, but it's not the same thing. So the idea is, delta is small where the Monte Carlo is most active. So at small PTs, there are lots of emission, and therefore you want delta to be small because this cross-section there is then highly suppressed. So this is the reason why you suppress H events at small PT. Conversely, when delta is large, then this is the region where the Monte Carlo is less active. So there are no or few emissions with the done with the Monte Carlo, and delta is such that it doesn't change the formal properties of MC at NLO. And if this sounds like delta is a non-emission probability, it's because it is a non-emission probability, or rather, it is constructed with non-emission probabilities taken from the Monte Carlo. So in picture, this is the situation. This on the left is the situation in MC at NLO. On the right, you have what happens in MC at NLO-Delta. So this blue curve is brought up, and essentially all of the negative weights in this region here are deleted before starting the shower. Okay, so this implies that your events, your hard events, will have a much smaller number of negative weights with respect to MC at NLO. So as I said before, delta is constructed by no emission probabilities, which are provided directly by the Monte Carlo. So the formula is here. I will not go into the details here, but I just want to stress that all the legs in principle contribute, all the bond level legs contribute. So you have a suppression for each of the legs, although in practice, for each event, only one leg is the one that dominates the suppression. The formal properties are that the integral of any distribution in MC at NLO-Delta is strictly the same as in MC at NLO, and is also strictly the same as the NLO cross-section, the fixed order one. The expansion in order alpha has the same properties as in MC at NLO, so they differ by order NNLO and beyond with respect to the fixed order prediction. And in the higher regions, the shapes of MC at NLO-Delta, MC at NLO, and the underlying Monte Carlo are the same. So essentially, you resum the logs in more or less the same way. So the structure is that, essentially we use PTI8. Of course, it could be another Monte Carlo, but we did it with PTI8 to pre-tabulate the non-emission probability. MAGRAPH will scan the phase space and generate the kinematics. The kinematics is given back to PTI8 that returns the stopping scales and the information on the dead zones. Using this input from PTIA, MAGRAPH will construct delta and integrates the cross-section, then unweight the events and write them onto the Lesuch event file, and then give those to PTIA to shower. Essentially, therefore, you have a unique executable that links MADGRAPH and PITIA in the same place at variance with what happens with MC-NLO. So these are, just a few results. And as you see, if you move from left to right, the situation is the situation improves in a sense that, you reduce the negative weights with folding. These are the numbers here, 111, 221, 441. The meaning is that the larger the number, the more folding you do. So you expect to reduce the negative weights. And then from MC-NLO to MC-NLO-Delta. So the ideal situation is the one on the last column. And as you see, all the costs are less than 2, bar for this case here, which is HBV bar, which is a very complicated case. I mean, one starts with MC-NLO, which is a cost of 27, which is a huge number. Still, it's reduced by a significant factor because you go down to 7.2, which is still a large number, but okay. I mean, it's still a progress with respect to what we had before. I'm pretty sure there is still something to be understood here, but we are working on that essentially. Okay, so these are for the rates. For shapes, essentially you see what you expect, namely that in small PTs, this is for Dralian. At small PTs, the shapes are the same. At large PT, both shapes and rates are the same. The differences are in the intermediate regions, where you do expect them, because this is the region which is not really under control in any matching formalism. I mean, this is the matching uncertainty, essentially. So if you take any matching formalism and really assess the impact of the matching uncertainties, this is more or less the ballpark you get. Okay, since I think I'm running out of time, let me skip the other and go to the conclusion.
You have another couple of minutes, Stefano, 2 or 3 minutes.
Okay, so I mean, the other things show more or less the same story. I mean, the Higgs case is completely identical to Dralian. TT bar is, on the other hand, showing much larger matching uncertainties. I mean, we were careful to verify that this is indeed compatible with the native matching uncertainty. So this is still within the uncertainties. And this is, of course, will be tested against data as soon as this will be feasible. Another couple of examples. I mean, here you have WJet production. Here you have WTT bar production. WTT bar production is probably the first case where we see an evidence that the multiple scale assignments in MC-NLO-Delta is more sensible than the one in MC-NLO, because the convergence, in quote, towards the fixed order result is faster in MC-NLO-Delta than it is in MC-NLO, okay? This is particularly striking because this process here, WTT bar production, is very, very massive, and therefore you expect the two things to converge at very large scales. And the fact that this happens at relatively smaller scale in MC-NLO-Delta than in MC-NLO is, in a sense, reassuring, because you don't want to go to the Planck mass in order to see this convergence. Okay, so so far so good. We didn't see any particularly striking case of things that are obviously broken. Still, and what I stress is that MC-NLO-Delta is a new matching formalism, and therefore it requires testing. I mean, if you think about the learning curve in the old days when the first matching and NLO matching were introduced, I mean, it took years, right? Now, this case will not take years, but still, I mean, it requires some understanding before declaring that everything is fine. The advantage with respect to MC-NLO is that there is, of course, a significant reduction of negative weights and therefore smaller event samples. There are more physical scale assignments, and this is something I didn't talk about, but it's an important thing under the hood is that there is a reduced sensitivity to the Monte Carlo, the approximations that the Monte Carlos do in the soft limits, which is generally a region where the Monte Carlos do not perform particularly well. The disadvantage is, of course, that you have longer running times. Of course, this is up to the detector simulation, because then you gain time at the level of detector simulation, because you have less negative weights and less events, essentially. So it's a trade-off, of course, which we believe would be an advantageous trade-off in all cases. So in MATRA-5 MCT-NLO, we have implemented the folding on top of the delta procedure for both MCT-NLO and MCT-NLO-Delta. So also in MCT-NLO straight, you can reduce the negative weights by folding. And the Lesush event file format has been modified in order to take into account this multi-scale structure of MCT-NLO-Delta. And we are still considering alternative option. That is, we believe there is a version of folding which is more complicated than the one implemented here, but could potentially be, quite a game changer, because it has the potential to reduce strictly to zero the number of negative weights in the S events. But this is to be confirmed. All right, thanks.
Thanks a lot, Stefano. This was very interesting and also very promising. I see that there are a lot of questions from me, F, and Josh on the Google Doc, but I don't know if there's other people also who want to raise their hand. Otherwise, Josh, maybe start with your questions. I think it's easier if you actually read it yourself, so you say exactly what you have in mind.
Yeah, so I have a sort of more philosophical question about that goes right back to the beginning, Stefano, where you were saying that giving up on higher precision should be avoided just because of negative weights. So, and I'm afraid it's not really a question MCT-NLO-Delta at all, but I was wondering if you had a feeling on whether you had significant concerns about doing something like, well, for instance, what's about to be proposed in the following talk, but also, which is the resampling algorithms, but also about reweighting a lower precision leading order multi-leg sample, for instance, to NLO predictions. If you do that before simulation, of course, you could still benefit.
Yeah, which is not, which is not the same thing as giving up on precision, right? I mean, you just, find different ways to hopefully keep the same precision by, and at the same time reducing the computing time. So, what I had in mind with that comment was essentially going back to the old days of, leading order simulation and things. Now, reweighting leading order simulation implies a reduction of accuracy if you cannot prove that the accuracy is kept, which means that you have to do your own work and show me that, by this reweighting, you perform well for all observables and in all cases, or, for a given process of interest. If this happens, then, of course, it's a possibility, but one needs to be careful, because this proof is not trivial, right? I mean, it's potentially, strictly speaking, is impossible to give, because the next observable you invent, then you have to prove it all over again, which implies that you have to rerun the NLO as well, because you want to compare with that, NNLO or NLO or NNLO or NLO merged. So.
Mm-hmm. Okay. Yeah, I mean, certainly it's hard to prove. I see Ben has his hand raised. I don't know if it's response to this, maybe.
Yeah, I was just very quickly. I think that I agree with everything that Stefano said, and maybe just to add, Josh, even in the reweighting case, in which I'll talk about in more detail, it's essential that you have the precision higher order calculation that you're going to reweight to, right? So even if you're not going to use it, through detector simulation, you still need it, and it's essential that it's as precise as possible. So I think I agree with the sentiment that we shouldn't be scared of negative weights, and I think that what I'm going to talk about is sort of very complementary to what Stefano talked about, and there's like a very clear, like they're both can be used the same. You can use both, right? It's not one or the other kind of thing.
Yeah, I mean, even if it's just at event generation level only, still it would be beneficial to have the reduced negative weight fraction, right? Even if we were to then use it to reweight something else. Okay, thanks a lot.
Okay, there's a few other questions. We're actually running a bit late, but let's go on with a few questions. I had one question, which is, you said delta does not change the formal properties of MC at NLO, and actually, so I had the impression that your formulas were kind of invariant under different choices of delta, but maybe I'm wrong. So I was just wondering, I mean, you said that you are using actually a very specific choice of delta, which is that formula with the product. Can you actually, do you have some flexibility? Can you use a more arbitrary deltas just to suppress further negative weights, or am I completely wrong?
So there are two things here. First of all, let me go back to this one. Now, the formal properties I alluded to are, preserved if you have these four conditions. Okay, whatever function you invent that has these four conditions, that obeys these four conditions, will be such that these three properties will be like this. Okay, now these are formal properties. Okay, it doesn't tell you that the coefficient in front of this alpha strong to the NNLO is 1 or 1.5 or 2 or whatever. Okay, so there are, within that class of functions for delta, there are good choices and less good choices. The one we came up with, took a while to figure out. And it was essential for us that most of the information that entered that function were provided by the Monte Carlo itself, because we want to mimic as closely as possible the Monte Carlo we interfaced. Having said that, you can do the exercise of constructing the delta by simulating the delta entirely with analytical properties. So you take the simplified analytical Sudakovs and you use those. And the properties, the formal properties I'm showing you in slide 18, will be exactly the same. But the physics, namely, the specific observable for the specific process, will change. I mean, will change by, I don't know, 5%, 10%, 20%, whatever, but change it will. So, it's important to distinguish between the formal properties that identify a class of delta functional forms with those that you want to use in order to do the best job possible at the level of physics, which we believe must be dictated by the Monte Carlo you interface to. So the day you interface with Herwig, say, you want Herwig to provide you with the scales and the Sudakovs.
Thanks a lot, Stefano. Yeah, I understand better now. I see one raised hand, but maybe okay. Efe, you want to ask your question?
No, I think we can continue on the Google Doc for my questions, and we can take the raised hand, I think.
We take the raised hand, okay. So, Sumyadeep, you have a question?
Can you hear me?
Yes, not very well, but speak up, please, a bit.
Okay, so I have just a naive question. Is this module already officially released by MATLAB, or it is still in the development process?
It's in the beta version.
Okay, so could you please tell me when it will be released officially, or?
Well, I mean, it's a bit hard to give you a time scale, because there are lots of small technical problems related to, for example, the pre-tabulation of the Sudakovs, the way in which the executable is constructed by linking PTIA and MC at NLO. What I can tell you is that the first step has been done on the PTIA side, because they released the version which has now all the internal routines that we have developed for setting up MC at NLO-Delta. So this is something that is already available. I mean, of course, it's not the whole thing, because you lack the short distance cross-section information, but it's a first step. And we are working on the rest, of course. As soon as we are ready to go, that we are confident that all the technical problems have been solved, then this will be released with the usual channels, namely on Launchpad.
Okay, and the last question. In the final version, there will be MC-NLO and MC-NLO minus delta. Both the module will be present, or
yes,
is there any...
yes. This is another reason why the release of this version is complicated, because MC-NLO-Delta was developed in a version that was not able to do also MC-NLO, and therefore to merge the two versions, we discovered lots of overlapping things and potentially conflicting things, and therefore we had to sort them out. So this is the reason why, one of the main reasons why there is a delay in the release. But yes, the final version will have the two of them.
Okay, thanks.
Yeah.
Thanks a lot. I don't know. There are still a couple of questions on the Google Doc. We are a bit late. I don't know what people.
I think, Andrea, it probably makes sense to. I mean, we can, in general, we can continue the discussion after the event via the Google Doc and via email if need be. So maybe we just continue.
Okay, so maybe we just continue with Ben's presentation then. So thanks a lot again, Stefano. This was very, very useful, and I think we'll maybe continue some discussion offline. So